Welcome to this explainer. We're diving straight into one of the wildest engineering challenges out there right now, building massive structures for literally the most extreme environments in the universe. Think deep space, lunar bases, or even those next-generation fusion reactors. You see, when we push human exploration that far, we're basically picking a fight with the fundamental laws of physics and chemistry. The materials we use every day here on Earth, they just don't act the same way when you launch them into the cosmos. So how do we actually build the future when our standard building blocks completely fall apart? Let's get into it.
So here's the really big question. How do you build a spacecraft that won't just shatter when it hits the extreme cold of deep space? And when I say cold, I mean ultra-low temperatures dropping below 20 Kelvin. To put that into perspective, that's roughly minus 423 degrees Fahrenheit. At those insane temperatures, conventional metals go through a massive shift. They just become incredibly brittle. Take classic martensitic stainless steels, for example. Their impact toughness literally plummets, turning them into a huge liability for brittle fracture. Or look at 9% nickel steels. Sure, they might stay somewhat tough, but they shrink and warp because of horrible dimensional stability. Honestly, it's a material science nightmare.
Which brings us to Section 1, Materials for Extreme Cold. To actually survive these deep freeze conditions, scientists realized they needed an entirely new class of material. And that brings us to this beauty right here, the Mo5 complex concentrated alloy. Let's compare this to those conventional alloys we just talked about. While traditional metals are out there getting brittle or warping at 77 Kelvin and below, this Mo5 alloy is doing something almost like magic. It's a hyper-specific mix: cobalt, chromium, iron, nickel, and exactly 5% molybdenum. And it uses something called a transformation-induced plasticity, or TRIP effect. Basically, as this metal deforms under the intense stress of extreme cold, its internal structure actually transforms to become stronger and more ductile. It literally fights back against the cold. It's a bona fide supermetal for cryogenic engineering.
But there's a catch. Section 2, the CCA Welding Challenge. Okay, having a tiny piece of the supermetal in a lab is cool and all, but it's totally useless if you can't weld giant sheets of it together to, actually build a spaceship or a massive fuel tank. And here is the brutal irony. The exact same thing that makes these complex concentrated alloys so incredibly strong? Yeah, that's their absolute kryptonite when it comes to welding. Because these alloys are a complex soup of different elements, hitting them with the intense, localized heat of a welding torch causes severe elemental segregation. The elements literally separate out because they all have different melting points and diffusion rates. So what happens? You get hot cracking, you get massive solidification defects, and you get these highly brittle intermetallic phases forming right out of nowhere. Joining two pieces of this stuff together without destroying its structural integrity is a mammoth metallurgical challenge.
So, what's the workaround? The solution is precision laser welding. The researchers quickly realized that traditional arc welding was just way too messy. The heat spreads out too much. They needed something way more surgical. Laser welding gives us this super high energy density beam that creates a tiny, rapidly moving melt pool. It dramatically minimizes the heat-affected zone around the weld, cuts down on distortion, and crucially, limits the actual time the metal spends in that dangerous, chaotic melting phase. But here's the thing, even with a laser, you can't just point it and pull the trigger. You have to dial in the exact right settings.
Let's look at Section 3, the Goldilocks laser parameters.
To actually conquer this Mo5 alloy, the researchers had to go on a meticulous trial and error quest. They were looking for that perfect balance. Not too hot, not too cold. The literal Goldilocks zone for laser power and welding speed. Just take a look at all these cross-sections from their beat-on-plate trials. They tested laser powers ranging from 0.4 up to 0.9 kilowatts and speeds anywhere from 15 to 40 millimeters per second. And man, you can see the failures perfectly laid out here. Up in the top right, when the laser power was cranked too high, the extreme heat made the metal literally evaporate and flow backward. It created what's called an underfill, which is basically a giant trench carved right into the metal. But then look down at the bottom left. When the energy density was too low, the metal didn't even melt all the way through, and that left these huge gaping pores and root dropouts. Just a mess.
But out of that massive grid of failures, two absolutely perfect, defect-free conditions emerged. These were our finalists. The first one was welding speed of 15 millimeters per second paired with a laser power of 0.6 kilowatts. The second was slightly faster, at 20 millimeters per second with a slightly higher power of 0.7 kilowatts. Both of these produced gorgeous, full penetration welds with zero macroscopic defects when looked at under an optical microscope. So with these two parameters locked in, the researchers moved on to the ultimate test, butt welding two actual solid plates of this Mo5 alloy together.
Which brings us to Section 4, inside the weld microstructure.
All right, to figure out which of these two finalists is actually the true champion, we've got to do some microscopic detective work. Let's dig into these hardness graphs. What you're seeing here maps the physical hardness of the metal straight across the actual weld joint. Now, on the far left and the far right of both of these graphs, you see the base metal sitting strong at about 350 on the Vickers hardness scale. But right there in the middle, the fusion zone where the laser actually melted the metal, the hardness drops off significantly to somewhere around 200 to 250. Now, that drop is totally expected in welding, but take a really close look at the difference between the two. The 20 millimeters per second condition on the right, it shows a much more erratic, separated profile between the upper, middle, and bottom sections of the weld. But the 15 millimeters per second condition on the left, it's much more uniform. The thermal profile there preserved the mechanical properties in a vastly more balanced way.
Now, let's zoom in even further. I'm talking right down to the cellular level, inside the weld itself. Because as the weld cools down, the metal crystallizes into these cellular columnar structures. The image on the left is our 15 millimeter per second weld, and the right is the 20 millimeter per second weld. You can visibly see it, right? The 15 millimeter per second weld on the left created significantly finer, smaller cellular substructures. The thermodynamics happening here are just fascinating. Because of the very specific balance of laser power and fluid dynamics in that melt pool, the temperature gradient was gentler, and that allowed these much tighter, finer cells to form during the rapid solidification process.
And the actual size of those cells, that's incredibly important because of what lives right on their borders, the mu phase. So the mu phase is this highly specialized molybdenum-rich precipitate, and it forms exactly along those cell boundaries as the weld cools. Think of the mu phase almost like microscopic scaffolding. By surrounding the cells, it physically reinforces the metal. It heavily enhances its slip resistance and overall strength, and that is exactly what we need if this material is going to survive the intense, crushing stresses of a cryogenic environment. So the math here is pretty straightforward. More scaffolding equals a fundamentally stronger weld. Because that 15 millimeter per second condition created a much finer cellular structure, it literally provided more boundary area for this mu phase to grab onto and precipitate, and the data backs this up perfectly. The 15 millimeter per second weld allowed for a robust 7.0% mu phase area to form. Meanwhile, the 20 millimeter per second weld only managed 5.0%. So that slower, slightly lower power weld is actively building a vastly superior internal architecture.
All right, Section 5, the winning weld. Okay, the data is all in, and we are finally ready to crown the ultimate champion of this metallurgical showdown. And honestly, if you needed one final absolute slam dunk piece of evidence, just look at this number, 7.3. See, the researchers put both of these welded plates through an X-ray computed tomography scan. Think of it like a 3D medical CT scan, but for solid metals. They were looking for microscopic pores hiding deep inside the fusion zone. And what did they find? The 15 millimeter per second at 0.6 kilowatt condition had a total internal pore volume that was a staggering 7.3 times lower than its competitor. We're talking just 0.0092% porosity versus 0.0677%. It frankly wasn't even close.
Let's quickly recap exactly why the 15 millimeters per second at 0.6 kilowatt parameter is our absolute Goldilocks condition. First, it produced a noticeably finer cellular structure. In turn, that tighter structure allowed for a significantly higher precipitation of that protective, scaffolding-like mu phase. On top of that, it featured a wonderfully smooth, uniform hardness profile from top to bottom, and of course, it boasted an incredible 7.3 times less internal porosity. Honestly, finding this exact combination of laser speed and power is like finding the cryptographic key to unlocking Mo5 CCA for actual real-world manufacturing. Which leaves us with a totally thrilling prospect. Now that the welding code for this incredibly stubborn but amazingly strong supermetal is finally cracked, what deep space frontiers will Mo5 CCs allow us to reach next? We literally now have a realistic pathway to build massive liquid hydrogen fuel tanks, next-generation fusion reactors, and interstellar spacecraft that can genuinely withstand the brutal freezing void of deep space without shattering into pieces. The materials of tomorrow are literally being perfected today, one precise laser beam at a time. Thanks so much for joining me on this explainer, and keep your eyes on the stars.